Welcome to Under the Microscope, your go-to podcast for materials and nanoscience. I'm your host, Dr. Pranatik Sirsagar. With each episode, I introduce you to a scientist working in the field of materials and nanoscience. Together on this podcast, we explore the fascinating world of nanoscience, where the smallest discoveries make the biggest impact. Make sure that you are hitting that follow button on your favorite podcast app. And if you're watching on YouTube, yes, the video of this podcast goes on YouTube channel of the Science Talk. So make sure you hit the subscribe button. There are multiple different ways of showing your support for the podcast, and subscribing and following or even leaving a review is the most easiest and the most convenient thing for you to do. I'm also going to put the link to the newsletter of the Science Talk, which you can also sign up for. All of these links that I'm mentioning are in the show notes and the episode description. All right, let's get into today's episode. Welcome, Brian, to Under the Microscope. How are you?
Yeah, I'm good. Thank you. Thanks for the invitation to be here. And it's nice to meet you.
Very excited to take a deeper dive into your research career journey and all of that good stuff. In addition, what your plans are with the QuanTour light source. Let's start with understanding your research. So could you please explain your research to us in super simple words, please?
So in my group, we design and we make quantum devices of different types, so different materials. Some like the QuanTour source are 3-5 quantum dot. And then in other cases, we use 2D materials, and we collaborate closely with colleagues who work with silicon carbide or diamond or rare earth ions doped into crystals as well. And so what we try to do is, in these devices, engineer the properties of single particles, such as electrons or particles of light called photons. And also we try to engineer and probe the interactions between these particles. So not just having one electron, but maybe a few or many that are interacting together. And this can give rise to new types of phenomena like magnetism, stuff like this. And so our goals are to use these devices to understand sort of how these phenomena work in these materials, and hopefully eventually to exploit these into new types of technologies.
You fabricate all these different kinds of material devices and investigate the interactions from the fundamental physics perspective to have the next generation of technology, say, or emerging technology with magnetism. Okay, help me understand this a bit. With the QuanTour project, we have had relaxed quantum dot, stressed quantum dot, the pyramid quantum dots. We have also had the quantum communication, theoretical aspect, experimental aspect. Where does that fit in with your research? So help me understand that a little bit.
So my background, for instance, is in strained quantum dots. So I started out making them and then basically learned how to do spectroscopy and quantum optics on these. And we use these still in my lab. The skills that we learned in working with these types of materials, the things you care about when you do spectroscopy, how to build the optics and make sure you squeeze every particle of light you can out of your setup and structure, and things like that sort of overlap into these other material platforms, which we've started to work with as well. Each material and different platform has their own advantages and drawbacks. And so it's definitely the case that no one material is the material of the future, especially when it comes to quantum applications. We use the similar techniques to both engineer the devices, but also to probe them. And it's almost always, in our case, using optics to probe these materials.
You also mentioned the 2D materials. Are we talking then about the hexagonal boron nitride? Because that is something that Carlos and Moire also spoke about. So not just the gallium arsenide ones, the strained ones that Ronaldo mentioned. He is using a magnetic field to align all the quantum dots in whichever direction that we want. Similar to what Emmanuel from Cork, he also mentioned that. But in his case, it is more about the site control. So when you talk about the different materials, are you then referring to any other 2D materials that are as good as boron nitride for the quantum communication?
I don't want to compare them like an arms race, right? Not one's better than the other. They have different features that make them better. We work with semiconducting 2D materials. Boron nitride is essentially an insulator, And actually in a lot of devices, it's basically used just as an insulator, just as like a tunnel barrier or an encapsulating type of material. Whereas graphene, is semi-metal. And then there's also a large zoo of 2D semiconductors. And maybe the most popular are materials called transition metal dichalcogenides. These are materials that have a heavy metal atom in the center and then a chalcogen atom above and below it.
Mm-hmm. What is chalcogen atom?
Like selenium or sulfur.
Okay.
Those are maybe the two most common. And the heavy metal could be something like tungsten or molybdenum. Those are the main ones. There's many, many more. It's sort of famously discovered with the sticky tape, where you could peel off individual layers from graphite. So they have really strong bonds in the planes and very weak bonds between the different layers. So you can sort of mechanically pull them apart. There's a big zoo of material. Boron nitride is one. It has a very wide band gap. Some groups have really been trying to push looking at single defects in those wide band gap materials. So it's sort of a good isolated host for a single electron, let's say, similar to a quantum dot in a way, but it's a defect in the lattice that creates that site to trap the electron. In the semiconductor materials, you can also have defect, but they're lower energy band gap. So what you can do is try to engineer heterostructures similar to what happens in the strained quantum dots, right? Or even in the unstrained quantum dots. There you have like indium arsenide surrounded by gallium arsenide, and then the indium arsenide is a lower band gap, and so the electron or the hole get trapped in that region. So in similar examples, we can sort of engineer structures where we can trap electrons or holes in these semiconductor 2D material. And so we spend a lot of time doing that. And I don't know if I should break out my props. We have an example.
You should. And for everyone who is listening on Spotify or Apple Podcasts, please check out the video of this episode on YouTube, because Brian is gonna take out his props now to explain his research.
So this is representative of a sheet of atoms. Okay.
I see a graphene honeycomb lattice.
And if we pick another sheet of atoms and we put them together, and then we control the twist, you can see all these
Moire patterns.
Exactly, Moiré patterns, right? So you have this new in-plane pattern forming, and it's dependent on the twist angle between these two sheets. So what's actually happening is, as they change their atomic arrangement, have different electronic interactions. And so you can actually engineer these. If you have the right twist angles, you can create electronic modulation, and the electrons see that and they want to sit at the minima of these potential wells. And so they get trapped in these sites. These work out to be on the order of 10 nanometers spacing between them. And so whether or not they're good for quantum light sources, I mean, they can behave as a quantum light source. That's maybe not their strength. The maybe strength comes from the fact that they're very close together, and these particles in there can feel the interactions with the other ones. That's what's unique about this system.
You also mentioned that you want to exploit these materials and their interactions on atomic or electron level for emerging technology. Can you please explain to us what kind of technologies? Is it to make my phone faster? What is it for? What kind of emerging technologies are we talking about, or are we aiming for here? Or are you aiming for?
I think inevitably these materials will end up in technologies. I think it's very hard to predict. So for instance, Intel has on their current roadmap for transistors using these transition metal dichalcogenide semiconductors to make transistors. Whether or not that happens, I don't know. Most likely these will end up in technologies, probably quantum technologies if they ever really take off. That's maybe a topic for a debate for another day. What we're trying to do is a cross between fundamental and applied physics, and inevitably the advances in these topics end up in future technologies. So there's a former professor of mine, Herbert Kromer, who won a Nobel Prize in maybe 2002, something like that. He invented the heterostructures. That's when you take two materials and stick them together, and it really controls the sort of energetic landscape of particles in these materials. When he was doing that, he was just sort of doing curiosity-driven research. He didn't know that we'd all have these heterostructures in our pockets, in phones, communicating via satellites, right? He couldn't envision that. As we learn how to control properties of particles better, how to control their interactions, they'll end up in new technologies. There's lots one could dream up. So you could, for instance, make a transistor based on interactions. So something called a MOS transistor. If you imagine taking this Moiré superlattice and filling every one of these sites with the center with an electron. Because of the strong interactions between these electrons, no longer can you have conductivity. It stops the hopping of electrons between the sites, and that can function as a really good transistor. In principle, nobody's made a good one like that. And you just change it from a conductor to an insulator just by changing the number of carriers in these pockets. So in principle, it's a good way to make a transistor. Will that happen? We don't know. Will it be competitive with silicon transistors? Who knows?
You don't want to be the one who then comes on the season 16 of Under the Microscope and say, Pranoti, I told you 10 years ago this is going to happen.
Well, what I don't want is to be interviewed 10 years from now and you said, Brian, you said you'd have a quantum computer in 5 years, and then I don't have one. Oh, we can make lots of promises. I guess that's what happens if you read the introduction to any big paper or any funding application. What the game has to play, right? I guess we do it largely because it's a curiosity-driven topic, and we get to learn new things along the way. That's sort of the drive here.
And that's how also research and science works. You don't have an application in mind and then you reverse engineer it. It's discovery science. And then based on that, once you understand the property, because you never know what you will find when you're doing these kinds of experiments. You have some inclination or some idea based on the theory, based on your calculations, but at the end of the day, no one can predict, or rather, I don't expect you to predict that, okay, in 10 years, we are going to have this technology.
I guess we're driven by lots of the common things that we know would be beneficial for technologies. For instance, can we make coherent quantum states? Can we make them interact? All these types of things. But it's, at least in my group, we're maybe a little bit more closer to curiosity driven, although there's a lot of sort of applications that go into it. So we're investing heavily in understanding how to really take these two sheets of atoms and put them together in a pristine way. Initially, people were quite skeptical that you could put these two layers together, single sheets of atoms, and really have a clean interface such that you could really engineer the electronic states in these materials in a really clean way. But it is possible, but it's really challenging. We have a lot of applied technology that we're developing to perfect the way that's done, or to try to perfect it. But at the end of the day, we want to make new devices and see what happens.
That's why your department is called emerging technology, not we already know which technologies. I'm going to keep tabs on you and your research.
Okay. Sounded a bit spooky, but okay.
And in a good way, as to, okay, what kind of emerging technologies are coming now from Brian? I might just ask you like every second year, hey, Brian, let's do a podcast again. How does that sound? Put you under the microscope.
It sounds like a financial report to a funder, but in a much more friendly way.
It's in a much more friendly way, and it is coming purely from the passion and love and curiosity about science, and the research is basically coming from that and understanding like, oh, so what did you discover this time and in the last 2 years or so? It's in a friendly way. The funding agencies can do but for me, it's more for my audience. This is really interesting. I think on the QuanTour, I should really give props to Doris and Toby for picking all 12 of you QuanTour heroes. Let's talk a bit about your career journey. I want to imagine like a 5-year-old or a 10-year-old Brian playing outside and riding his bike and maybe thinking, I'm going to be a professor in Scotland. I'll be working on the emerging technologies that are going to change the world. Please tell me about your career journey so far.
Yeah, well, I don't think I understood what a professor was probably until I was about done with my undergraduate. I grew up in Indiana, enjoyed science and engineering. So I ended up applying to Purdue University, which is the best engineering science school in Indiana. So I did my degree in material science. It was a bit old-fashioned at the time. I did some undergraduate research along the way, and then came to the end and said, I like research. One of the professors at Purdue had recently come from Santa Barbara, where he did his PhD. So I applied to UC Santa Barbara and ended up there for my PhD. I started out as a sort of MBE grower, so similar to some of the other QuanTour heroes who grow these 3-5 quantum dots. That's sort of how I started my PhD.
Molecular beam epitaxy for anyone who did not get that.
We didn't get it, molecular beam epitaxy. So it's really more about making the samples. I was making lots of samples and sending them to my professors' collaborators around the world. And I wanted to spend more time understanding the physics of what they were doing with these samples. And so I transitioned into the spectroscopy. And then I did a postdoc with Richard Warburton, one of your other QuanTour heroes. He was here at Heriot-Watt when I came here many years ago now. I focused more on spectroscopy and towards quantum optics, working with him, like another PhD. So I went from growth to spectroscopy, and then I'm still here many years later. Certainly didn't set out to live in Scotland.
That is something we have in common. Both of our undergrad is in metallurgical and material science engineering, because back when I was doing my undergrad studies in India, Department of Material Science was heavily metallurgy. So I learned how to do the smelting and the forging from mines to manufacturing these steel bars. Were your parents academics?
My dad's a mechanical engineer. I went to study engineering. In hindsight, I probably had an inclination towards physics. I didn't know people went and studied physics. It wasn't a thing I thought of in high school, whereas I had lots of examples of engineers around me. And so I went to study engineering.
And what did your dad say, or how did he react when you decided to, let me make it very controversial. It wasn't that dramatic, I'm sure, when you decided to leave engineering to pursue physics?
I don't think it was about the topic. I think it was when I said I want to go do a PhD. And then when I never left the university, it's like, when are you going to get a real job? There's sometimes a stigma that you know too much about too little, which I don't think is the case for PhD, but there is that stigma. And I guess they probably also wondered if I'd ever get a job and that sort of thing. Doing a PhD is also a way to prolong additional responsibilities. I mean, it's not the right reason to do a PhD, but it often happens.
Your dad and my mother share the same opinion. She's like, now you're done with your PhD. Yeah, after the first job. Oh no, after the second job. Oh no, and now I'm starting my own company. I can't come back now. And my mom is like, you're just prolonging the time. And you're right, PhD is sometimes seen as in a fun way. We are all joking here for listeners and watchers, joking here. I'm going to put you on the spot and ask you to pick one research project that you're most proud of and explain it to us in simple words in the section we call In Other Words. One, okay? One.
Okay. It's a bit like asking which of your children you like best, right?
I know.
And I've learned with my kids, I shouldn't answer that question.
Let me make it easier for you. Which experiment are you proud of today?
I'm kidding. So I guess as I've already sort of started discussing this sort of trick.
The Moire pattern. Listeners, he has pulled out his props again.
Well, we'll go back to the Moiré pattern. Recently, we've been working with this, and we didn't set out to do this. It was sort of a surprise, and it was motivated by what a few other people had discovered. Initially, we were looking at these Moiré patterns to generate quantum light sources. So when the electron hole collapse, they spontaneously emit this photon. So we were looking at these materials for these photons, and then we understood that we should see these correlations amongst the particles in this lattice as well. So what we can do is change the number of electrons or holes that sit in these sort of Moiré potentials, and we can study how they interact, and we can even change the numbers, and we can turn a material that's not magnetic at all, and just by changing the number of electrons that sit in these, we can make a magnetic material. So I think that was quite cool. And not only that, but we can actually just probe that with light as well. We can just send in light and see how the light is absorbed in these samples, and we can measure the magnetism that arises. Intrinsically, these materials aren't magnetic at all. You dial it up to the right number of electrons, and you can make it magnetic and probe that with light. And also you can play with the energy levels and turn the magnetism on and off. It was really cool and lots of fun.
So you basically turn non-magnetic materials into magnetic materials.
Yeah. The materials themselves aren't magnetic, but the particles in the materials are magnetic. Yeah, that's essentially what happens. It's very similar to what, if you've heard of like magic angle graphene. So that's 2 layers of graphene, which you did your PhD on. So, graphite is non-magnetic. You put them together at a special angle, and you change the number of electrons sitting in these sort of Moiré puddles to just the right number, the fractional fill-in. You can turn something that's completely non-magnetic into something that's truly magnetic, or even superconducting in that case. And that also happens in these semiconductor materials, which is, kind of like magic. Just by changing the number of electrons, you can turn on and off the interactions and generate, magnetism.
There is the magic angle with graphene. So you have your material, you shine some magic in quotes light on it of certain wavelength at some energy, and then at some point they start showing your material, or the particles in your material start showing magnetic properties. Did I understand this correctly or oversimplified
It's
it?
close. There's a slight difference. We use batteries. We apply a small current to the material to control the number of electrons sitting in there. And then we probe these using optics, so using light. So the light isn't actually providing the carriers that then have some sort of spin order. Rather, we use a tiny battery for that, essentially, and then we apply a certain bias to the sample to create the electrons in this Moiré lattice, control really precisely the filling of the Moiré lattice, so the fractional filling. And then we can probe that using light. So one could also probe it using transport measurement. Inevitably, we have contacts in 2D semiconductors, unlike graphene, that have a little bit too much resistance. So it's been done by a few groups, but it's non-trivial to make good contacts. So instead of probing it using sort of transport measurements, we can probe it using optics.
Aha, so you're using battery and optics.
I would just call it an optical probe, right? So it's basically spectroscopy to probe what's happening to the electrons.
Right. And then you have magnetism that is, oh wow. What I want to understand from you, Brian, is that what else do you like about being a scientist? Because there are different aspects to you being a scientist, being a professor now as well. So what else keeps you in science?
Yeah, I think it's a combination of freedom to explore new things within a remit, depending on what you can get funding to do. And it's getting to do new things and learn new things, and it's the curiosity. And I think that's certainly what I enjoy most about it. That's probably what keeps me in it. Working with young people is good too. It sometimes can help keep me young. I'm starting. It's not very obvious, but it's starting to go great.
Don't see anything. This is all fake news.
That's getting great. Great ball. So very shiny in the video. Maybe I'll turn off the light. It's less shiny.
The freedom of doing science within certain frameworks, let's put it that way, and also working with younger, let's say, colleagues or younger students.
Yeah, younger and enthusiastic, and yeah, I think it's in many cases it's quite rewarding, right? Because a lot of creative people and they have good ideas, and yeah, it can be very exciting and rewarding.
Do you also have international students, like a lot of international students in your group or your department?
Yeah, it's mostly international. Yeah, so it's a very international group. So, or I'm not Scottish either, but there's normally just a few number of Scottish and then a few number of English or UK people in the group, and yeah, the majority are from somewhere else around the world. So we're a happy, diverse family, and that makes it fun as well.
That is so cool. That is so cool. I'm very happy to hear that. Working with younger, enthusiastic students or scientists or budding scientists, and the freedom to explore the realms of your understanding of physics and the research of it, I can relate to that. And those are the parts which often make me wonder, why did I leave science? Or maybe I should go back to doing the research.
We're not all perfect, right?
And speaking of which, what you love about being a scientist, what barely keeps you in science? So there are several parts, I'm sure, that work, that don't work whatsoever. But if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything.
Okay. So I think for the first one, it's maybe less for me, but at the same time, it sort of is. So it's that every PhD student gets to have like a eureka moment. So I think that's what makes science fun when you've been working hard to see something and you finally see that signal or get that result you've been wanting, or you get a result that you don't understand what it is for a long time, and then you keep probing it and teasing it out, and finally you understand it. And I think that's what makes science fun, and in the best cases. And my hope is that every student gets to experience that. And I know it doesn't always happen for every student. And that's a bit of a shame sometimes, I think, because it's a lot of hard work doing a PhD. And the hope is that every student gets to experience that aha moment. And at least for me, that's what I enjoyed when I started doing research. And I still get to experience these moments. Yeah, I quite enjoy that. So the goal would be, each PhD student gets their own
Eureka moment. Okay.
Yeah.
That is vision number one. Promote to go.
So I think more support for researchers. How about that? And I don't mean necessarily money. I mean technicians or engineers on hand to help them, especially in a lab where there's lots and lots of equipment and things are always breaking, at least temporarily, and require lots of interaction to get working. Or, we have to do lots of little engineering things ourselves, which every new student has to learn how to, many do at least, do a lot of coding, which is part of the job, and that's fine. But sometimes it gets beyond what we can do. Or even we had an example where we had to take control in Python, programming language, of a camera. It took like 6 months. We couldn't get the code from the company to control the camera. It's called Python wrapper to control it. And these things are really frustrating. And oftentimes it seems some students are just fighting noise in their experiments, like mechanical noise. And so more technicians or engineers to help solve small problems so that we can get on with the science.
Mm-hmm. Which they can solve maybe in a day, but for a PhD student or a postdoc, or even for you, it takes maybe 6 months. So it's just wasted time.
Yeah, that's right.
Which could be, that's a very good point. The support, of course, funding is always good. No one's going to say no to funding or less bureaucracy, but this is also a very good point that you raised, that technicians or engineers, support staff for running the lab, which is very, very important for experimental scientists, especially if you're working with equipment which is being customized. It is not on the market yet. That is wish number two. Eureka moment for PhD students and more technical support or technicians or engineers in the lab to run the experiments.
So I think the sort of reward system for science, it's all very competitive, but it's gone a bit askew. Oftentimes, if you read a glossy paper, it'll have some sort of outlandish claims and stuff like that. Similarly, if you read a big project, it'll have some outstanding claims about how it's going to change civilization. And it's good to think about these things, and that's what helps lead to progress. But at the same time, I think the competition drives it that way. At the end of the day, it's because few journals have too big of an impact on people's careers, and there's just not enough funding. So of course, people are going to say they can do something that is quite, in some cases, impossible. But that's okay. Most of the time, people use that to good effect. They use that funding to great effect, even if they don't deliver what they promised. But yeah, the promise one has to make in these papers and to play the game, I think isn't necessarily healthy.
Yeah, and I think that's a good point. And it's also, I would call you a more established sort of a professor or a researcher or a scientist, so more on the senior scientist based on your experience. And when there is a postdoc who is just starting out to build their group, then for them, it just feeds into their imposter syndrome, like, oh my God, the community wants all the questions answered. All the proposals that are funded right now, or the papers that are published, they're answering all the questions that I thought I would want to address. But then when they actually read it, and then it's like, well, actually not. Or in some cases it is. It's also daunting for the upcoming, let's say, professors or group leaders. So it doesn't help anyone, basically, to have this pressure and this level of competition. And also the monopoly, not in the sense that only one journal or one funding agency has all the control, but more like the system, the academic, the measuring the impact and the quality of research. I think that definitely needs to change. Also, for funding, more space for, we don't know what's going to happen, but this is an interesting fundamental physics question.
You have a good idea, and maybe it just requires a postdoc for a few years. That's almost impossible to get funded these days, at least in my experience. And rather, you have to join up and be part of a big political thing to get something funded oftentimes, or make a much bigger claim. But yeah, and it's a similar thing with the publication. So I think, or postdoc number of papers in a certain place to get a job sometime.
Yeah,
it's unfortunate. Everybody has to play the game to some degree.
Yeah, absolutely. And you're still playing the game, right? You're in the game. So you have more power to bring these changes for the next generation of scientists, let's say. So it's great to have people like you who are experienced and senior scientists who are thinking about all of these things, who are aware of these things, so that you can change the system from the inside.
We'll see what sort of power I have. Don't get your hopes up.
5 years and 10 years, we are going to come back together and be like, okay, Brian, how is that going?
Yesterday, I just had a meeting to talk about our research excellence framework, where each university gets assessed on their research progress every 5 years. So the next one's 5 years away. I had a meeting yesterday about this.
I'm not going to waste your time. But yeah, I hope all three of your wishes come true, and to some extent, maybe not 100%, but you never know. I really hope that next time you'll come on the podcast, your wishes are a bit like, well, actually, I have one more technician or whatsoever, or something like that. Or my PhD students had the eureka moment. But I think all these are kind of interconnected with each other, all three of your wishes. For the PhD student to have the eureka moment, they need to have a functioning equipment or a software or whatsoever, and also the funding and the publishing and all of that. I think all of these are interconnected. And I really have enjoyed speaking with you for more than an hour now. I have one last question for you. As you know, in addition to featuring on Under the Microscope podcast, you will also be hosting from the Blue Sky account with the same name, Under the Microscope, for one entire week when the QuanTour source is going to be with you. What can the followers of our Blue Sky account expect in the week that Brian is taking over the account?
Yeah, so I should first acknowledge my students, Fred and Sheena, who are really going to lead this. And I think I shouldn't spoil it, but I think you can expect lots of Scottish surprises. There are some stereotypes about Scotland out there. They may feature in this.
Okay.
On the Blue Sky account.
Okay, shout out to Frederick and Sheena. I will make sure to tag them when we are promoting your episode as well. What else? Cody told me that Doris and Toby are going to be with you in that week.
Yeah, so by pure coincidence, the QuanTour source is in Edinburgh at the same time as an international conference called the Single Photon Workshop is hosted in it. There will be, I believe, a lab tour at the end of the conference where, I don't know how many people signed up, but I understand that 2 70-seater buses have been hired to take people to the labs. So I don't know if we're really going to have 140 people in the lab. So it puts a lot of pressure on Fred and Sheena and Sasha to get the source working. And if we get it working, we might try and play a trick and change the color of the photon a bit like a magic trick, but we'll see. And it comes out of the QuanTour source, but we'll see. So that would be the other surprise. Well, I guess it's not a surprise anymore. So yeah, so for people coming into Edinburgh for this conference, they can get a QuanTour tour. Tour
with the QuanTour, or tour of the QuanTour. Okay, I'm running out of puns here, but thank you very much, Brian. This has been wonderful. Thank you for taking the time, and looking forward to your posts from Fred and Sheena, and also from you. And also already looking forward to recording with you in a few years' time. Thank you very much.
It's been nice to meet you. Thank you.
I hope you enjoyed this episode. And if you are not following the podcast Under the Microscope already, please do wherever you're listening right now. If you're watching on YouTube, please go ahead and subscribe to it. If you're listening to Under the Microscope on Apple Podcasts, feel free to leave a review. That would be wonderful. If you're listening on Spotify, do share in the comments. How did you like this episode? What were your key takeaways? And please do follow Under the Microscope everywhere. This is absolutely for free for you, and it means the world to me, and it enables me in bringing more and more amazing guests to you. Thank you, and see you in the next one.